Let's dive into one of the biggest, most profound mysteries in all of physics. What exactly are space and time? I mean, we think of them as the stage, right? The background where everything in the universe happens. But what if that stage isn't real? What if it's just an illusion, a projection from a much deeper, much stranger reality?
Now that's not a line from some sci-fi movie. That's a quote from Nima Arkani Hamed, one of the sharpest theoretical physicists on the planet, and believe me, he is not alone. A whole bunch of scientists are now convinced that our most fundamental picture of the universe, it's just wrong, and it needs a complete rewrite from the ground up.
So what's causing this crisis? Well, it all comes down to a massive clash between our two greatest theories of everything. We have one theory for the really big stuff and another for the really small stuff, and they just do not get along. And the battleground where they fight it out is the very nature of space and time itself.
Okay, so in one corner, you've got Albert Einstein's masterpiece, general relativity. It paints this beautiful picture of space-time as a smooth, continuous fabric, kind of like a cosmic trampoline that bends and curves when you put something heavy on it. That's gravity. But in the other corner, you have quantum mechanics, and it describes a world that is, well, it's fuzzy, it's pixelated, and it's all governed by the frankly bizarre rules of probability. Things don't have one definite spot. They exist in a cloud of possibilities. You just can't get two more different descriptions of reality.
And this isn't just a philosophical debate. This conflict comes to a head at the tiniest scale we can even imagine, the Planck length. When you get that small, gravity gets so intense that it has to be quantum. But when we try to use our equations there, they just completely break. They spit out nonsense, infinities. Einstein's smooth fabric of spacetime just dissolves into this chaotic quantum foam, where ideas like here and there literally stop making sense.
So, faced with this total breakdown, one group of physicists is saying, whoa, hold on a second. Maybe we're overthinking this. Maybe a revolution isn't what we need. What if space-time is perfectly fine, and we're just missing how it connects to the quantum world?
This is the argument from physicist Antoine Tilloy. He makes a great case for what he calls the boring option. Before we just throw out 100 years of physics, maybe we should make absolutely sure that space-time isn't fundamental, just like Einstein said, and that we just need to find the right way to plug it into all that quantum weirdness. And this brings us right to the heart of the problem for this, let's call it, conservative idea. How does something definite and smooth, like the grid of space-time, get pushed around by something that is fundamentally fuzzy and uncertain, like a quantum particle that's just a cloud of probability?
So, the first and most obvious guess was something called the mean field approach. It's pretty simple, actually. It just says that space-time doesn't really care about all the quantum fuzziness. It just reacts to the average position of a particle, its most likely spot. Seems reasonable enough, right?
Well, it turns out this simple idea leads to situations that are completely absurd. Take Schrödinger's cat, which is in a quantum state of being both alive and dead at the same time. This theory predicts that the live version of the cat would actually feel the gravity from its own dead, ghostly self. We have never, ever seen anything like that happen. So this boring option, at least in this simple form, is a total non-starter.
All right, so if the boring option doesn't work, that forces physicists to get a lot more radical. They started asking, what if the whole problem is our starting assumption? What if space-time isn't smooth at all? What if, at the most basic level, reality is digital?
And this is the core idea behind something called causal set theory. It says that reality isn't a smooth, continuous sheet. It's actually made of these tiny, distinct atoms of space-time, or events. And the only thing that's really fundamental is the relationship between them, the fact that event A happened before event B and could have caused it. That order is all there is.
One of the pioneers of this theory, Raphael Sorkin, came up with this brilliant little mantra to sum it all up. Order plus number equals geometry. What he means is that all the things we think of as geometry, like distance and time, they aren't fundamental. They just emerge from two basic things, the causal order of all those little events, and just counting how many of them there are between a cause and an effect. So here's the key takeaway. The smooth, flowing reality that you and I experience every day, it's really just an illusion. It's exactly like looking at a photo on your phone. It looks perfectly smooth, right? But if you could zoom in far, far enough, you'd see that it's actually made of individual, distinct pixels.
But if you thought that was a strange idea, you might want to buckle up, because there's an even wilder, more mind-bending possibility out there. And this clue comes from the most extreme places in the cosmos, black holes.
So back in the 1970s, Jacob Bekenstein and Stephen Hawking made this absolutely stunning discovery. See, normally the amount of information you can store in a place depends on its volume, its 3D space. But they found that for a black hole, all the information about everything that ever fell into it, it's proportional to its two-dimensional surface area, the event horizon, not its volume. It's as if everything was somehow smeared out and stored on the boundary.
This shocking result gave birth to what's known as the holographic principle. And the idea is as simple as it is staggering. If a 3D black hole can be fully described by its 2D surface, maybe the same is true for the whole universe. Maybe our three-dimensional reality is nothing more than a projection, a hologram, of physical processes happening on some faraway, two-dimensional surface.
Now, for a long time, this was a really cool idea, but it was pretty speculative. That is, until a mathematical model called the ADS/CFT correspondence came along. It's kind of a toy universe that finally gave physicists a concrete example of how this holographic idea could actually work.
Think of this ADS-CFT thing as a kind of dictionary or a Rosetta Stone. It lets you translate between two totally different but completely equivalent ways of describing the same reality. On one side, you've got a complex universe with gravity, called the bulk, and on the other, you have a much simpler quantum theory with no gravity, living on the lower dimensional boundary of that universe. They look completely different, but anything that happens in one has a direct translation in the other.
And here is the absolute bombshell. This model showed that the very geometry of spacetime inside the bulk, things like distance and what's connected to what, is directly mathematically equivalent to the patterns of quantum entanglement between particles on the boundary.
I mean, just let that sink in for a minute. In this picture, quantum entanglement isn't something that just happens in spacetime. Quantum entanglement is what creates spacetime. It's literally knitting the fabric of reality together. The more entangled two particles are out on the boundary, the closer together they are inside the bulk. Spacetime in this view is not fundamental at all. It emerges from quantum information.
So, after this whole journey, from conservative ideas to a pixelated reality to a giant cosmic hologram, where does that leave us? What is spacetime really?
Well, the hard truth is the case is still wide open. And the biggest problem is that we have no way to actually test these incredible theories. To really see what's going on down at the Planck length, we would need a particle collider about 1,000 trillion times more powerful than the Large Hadron Collider. We're talking about a machine roughly the size of the entire Milky Way galaxy.
And here's the final, almost cosmic irony. Even if we somehow manage to build that impossible machine, the sheer energy you'd need to smash particles together in such a tiny space would instantly create a microscopic black hole. The very secrets we were trying to find would immediately get hidden from us, trapped behind an event horizon. It's like nature has put up the ultimate privacy fence.
So we're left with this final, profound question that gets at the very foundation of reality. If the stage of our existence, if space and time themselves are not fundamental, then what is? Is it the logical chain of cause and effect? Is it the strange, spooky connections of quantum entanglement? Or is it something else, something we haven't even dreamed of yet? Whatever the answer turns out to be, finding it won't just change physics, it's going to change our understanding of everything.